sklearn, ensemble, hist gradient boosting classifier. Description. Hist gradient boosting classifier is a gradient boosting algorithm that utilizes histogram-based binning for efficient and scalable training. It excels at handling high-dimensional datasets and is known for its accuracy and robustness. Inputs. X a 2D array representing the features of the training data. Each row corresponds to a data point, and each column represents a feature. Y a 1D array representing the target labels for the training data. Outputs. Self-trained hist gradient boosting classifier object. Predict probX returns the probability of each class for each data point in X. Steps. Initialization. The algorithm starts with an initial prediction model, e.g., a constant value. Iterative boosting. The algorithm iteratively builds an ensemble of decision trees by calculating the residuals errors between the current model's predictions and the actual target values. Training a decision tree on the residuals. Updating the model by adding a weighted contribution of the new tree's predictions to the existing predictions. Regularization to prevent overfitting. The algorithm incorporates regularization techniques like L1 and L2 penalties. Metrics. Accuracy measures the proportion of correctly classified data points. Precision measures the proportion of true positive predictions out of all positive predictions. Recall measures the proportion of true positive predictions out of all actual positive data points. F1 score, a harmonic mean of precision and recall. AUC area under the ROC curve represents the model's ability to distinguish between positive and negative classes. Visualization plots. Feature importance plot depicts the relative importance of each feature in the model's decision-making process. Decision tree visualization visualizes individual decision trees within the ensemble, revealing the structure and decision rules. ROC curve plots the true positive rate against the false positive rate for different classification thresholds, illustrating the model's performance. Fine-tune parameters. Learning rate controls the step size at which the model learns from new trees. A smaller learning rate generally results in more stable training but may take longer to converge. Maxiter specifies the maximum number of boosting iterations, i.e., trees added to the ensemble. Max depth sets the maximum depth of each individual decision tree. Deeper trees can capture more complex relationships but may be prone to overfitting. MinSamples leaf defines the minimum number of data points required in a leaf node of a tree. This helps prevent overfitting by ensuring that each node has a reasonable amount of data. Uncertainty methods. Confidence interval provides an estimate of the range of possible values for the predicted probabilities, capturing the uncertainty in the model's predictions. Predictive entropy quantifies the uncertainty in the model's predictions by measuring the expected information gained from observing the true label. Challenges and fixes. Challenge 1. Overfitting. The model may perform well on the training data but generalize poorly to unseen data. Sample use case that resulted in challenge 1. When using a high learning rate and large max depth, the model might memorize the training data and fail to capture general patterns. Fixes to challenge 1. Reduce the learning rate. Decrease the maximum depth of trees' max depth. Increase the minimum samples per leaf. MinSamples leaf. Use early stopping based on a validation set. Challenge 2. Long training time for large datasets. Training can be computationally intensive. Sample use case that resulted in challenge 2. Large datasets with many features or a high number of boosting iterations may lead to longer training times. Fixes to challenge 2. Reduce the number of boosting iterations. Maxiter. Consider using a smaller subset of features. Feature selection. Utilize hardware acceleration e.g. GPUs. Explore alternative algorithms if speed is a primary concern.